All right, so welcome to our first video lecture. This is just our first lecture of two, maybe three that are going to cover review topics. We'll see how quickly we can get through them. Now, the statistics we're learning require you to understand a simple concept. That is that a sample comes from a larger population of data. And we're likely unable to ever actually collect the population of data. So let's take this example right here. My population of interest is all the mountain climbers in Denver, and all these little cubes represent all the mountain climbers in Denver. Now, in order to it might be impossible to find all these mountain climbers in Denver and measure their fearlessness, the thing I'm interested in. So what I have to do is I have to gather a small sample of mountain climbers so that I can make inferences about the entire population of mountain climbers in Denver. Now, if I had access to every single mountain climber in Denver, and I was able to get data from every single mountain climber in Denver, I would not need statistics that involve p-values. I wouldn't need statistics beyond means and standard deviations. All I would have to do was look at the means and see if they were different. I wouldn't need to actually calculate p-value based statistics, and I would be done. However, it's nearly impossible to get a population, so we have to use what we call inferential statistics, where we infer the population data from the sample data. And that's why it's so important. You need to realize that we are in this class making inferences about populations through data collected from smaller samples. This leads nicely to my next slide. There are two types of statistics, descriptive and inferential. Descriptive statistics are what you're used to. They describe our sample. They're the statistics you calculated in high school. Here's 20 numbers, tell me the mean, median, mode, standard deviation, things like that. They are very simple. They describe your sample directly. They require basic calculations. Here are some examples. I just mentioned them. And the only way to be wrong is to do the calculation incorrectly. Divide by 5 instead of 4, in a sample of 4 observations, right? Like, the only way to really mess these up and be wrong is just to do your calculations incorrectly. Now, descriptive statistics you should be comfortable with. Inferential statistics are something new. Well, inferential statistics infer population data from sample data. So keep that in mind, right? That's what it means. So we describe our population indirectly from our sample statistics. We use descriptive statistics to calculate our inferential statistics. They do require complex math theory. I won't teach you this complex math theory. This is an application class, but there is complicated math theory underneath the engine of these tests. Inferential statistics, you're familiar with them too if you're in the psych major. Anything with a p-value is an inferential statistic, essentially. And the interesting thing about inferential statistics, even if you calculate everything correctly, your conclusion could be wrong. Now, that's not saying that your math was wrong or you did anything wrong, but from an omniscient perspective of a God, you can conclude that there's no difference when there is one. You can conclude that there's a difference when there's not one. Very simple stuff, but essentially, descriptive statistics describe your sample. Inferential statistics use complicated math that we're going to learn in this class from a sample to describe a population, right? So that's inferential uses sample statistics and complicated math. Well, complicated for us, not complicated for mathematicians, right? To infer something about the populations we're interested in. Like previously, Denver's mountain climbers. Now, this is a review, so I'm assuming nothing here, but statistical variables are any observations that we turn into numbers. Maybe the observations started out as numbers, maybe they didn't. But I am a firm believer that anything can be turned into numbers. For example, I just learned that digital pictures are you can manipulate digital pictures by manipulating the numbers in a data file that contain all the little values for the picture. So anything can be turned into numbers. Now, if we have a picture of people with smiling faces, if I can identify the corners of the mouth and the lips, right? If I can match those up in the pictures, then I can determine the intensity of the smile with numbers. That's something that I'm thinking about working on, but that's the basic idea of making a statistical variable. I have a picture. How do I pull the numbers out of it? It's easy to see numbers in performance on a free throw shooting task, right? But it's hard to see numbers when they're not clear. Nonetheless, everything we do in this class is going to require every variable to be converted to a statistical variable. So here is an example of a variable where, it's just gender, traditional gender variable, where I have to convert it to numbers so I can do analysis on it. So I just say, man equals 0, women equals 1, transgendered man equals 2, transgendered woman equals 3, non-binary equals 4. I've just taken an open response variable, a categorical variable, we'll learn about that in a second, and converted it to numbers. So statistical variables are anything you convert to numbers, and there are 2 different classes and 4 different types of statistical variables. Discrete variables are just categories. Nominal is just names. Nominal means names. So a variable where the different categories just represent different names, like gender. That's a discrete variable. So in this example too, it's important to realize that, man, woman, transgender woman, non-binary, none of those are better or worse or have more of or less of than anyone else. They're just categories. Right? That's it. They're just different people. And that's how you have to view it, right? They're just different people, different names. Like if you, let's take this out of that example and go back to elementary school. If you were in the blue group or the red group and they were just there to split the class into 2, that's another nominal variable. Ordinal variables are just categories as well, but they're ranked categories. That's it. So here we have the example first year, sophomore, junior, senior, right? They're ranked, right? They have a class rank, right? They're in an order, right? But people in the junior category aren't specifically greater than people in the sophomore category. They're just people. A better example is sort of the chain of command. You got commander, you got generals, you got, I think it goes commander, general, commander, I don't know the rest, major, private, first class. Those are different people, and the person at the top has more power, just like the ordinal, the person with the classes, the senior has, been here for more years, but they're not really mathematically different. For example, just take the fact that intelligence, I've had sophomores that are way smarter than seniors. Time in, right? Well, you can be a junior with, I don't know, let's just say for the sake of argument, 60 credits, or you can be a junior with 66 credits or 68 credits. So it's not really quantified. There's just different groups, but they are ordered. Right? Those are your categorical variables. You're in different categories. If they're just random categories, they're nominal. No one's has more power, there's no order to it. They're just nominal. If there is order, it's ordinal. Super simple there. Let's move over to our continuous variables, our statistical variables. Now, the ratio is what you think of as a number, right? 0 means none. 1 and 2. 2 is twice the amount of 1. 3 is 3 times the amount of 1. 4 is twice the amount of 2. 2 is half the amount of 4, right? A ratio scale is just a numerical scale where 0 means the absence of. In terms of psychological research, one common thing we're interested in is performance. So let's just choose a task, number of free throws you make in 60 seconds. If you make 0, you've made no free throws and you have a 0 level of performance. 0 means the absence of made free throws. It's a ratio scale. Now, interval is basically a ratio scale where 0 does not mean the absence of. I'm going to give you my example here, 1 to 7. How happy are you? 1's extremely unhappy and 7's extremely happy. And there's intermediate values in the middle, right? Here, the important part is that 0 does not mean the absence of happiness. In this case, 0 is not even on this scale, so it's an interval scale. However, right, we assume that a person who reports a 2 on happiness is twice as happy as the same person when they report a 1. Now, I want you to focus on interval and ordinal, the two bottom ones. This is where your explanation really matters. I see the overlap here. Let's take that 1 to 7 happiness scale. I'm pretty sure that when I write a 7 on a happiness, or let me choose easier numbers. When I write a 4 on a happiness scale, when I write a 2, I'm definitely happier when I have a 4 than when I have a 2. Am I twice as happy? Not really. You could make an argument that that's an ordinal measure. Now, here's the reality of it. Once you learn the assumptions of our tests, you're going to realize that even though logically this may be an ordinal measure, we're going to have to assume it's continuous, because if it's not continuous, then we can't use the stats that I'm teaching you in this class. Now, I'm going to tell you there are other stats beyond this class. This is the intro to the class, right? So there are questions like this that aren't as clear cut, and I'm not going to lie to you, all right? The same thing with the sophomore, junior, senior example. Like technically they do have more credits. Technically, there are ways to think of this, at least time on campus, like a junior. Well, let me go senior. A senior has twice as much time on campus than a sophomore. You could make that argument. It's just a little messy. So I'm not here to lie to you about stats. I'm just here to tell you in the future, in this basic stats class, we're going to assume a measure like how happy are you on this 1 to 7 scale is a continuous measure, because we have to do our data. Likewise, we're not, as long as we're using, sophomore, junior, and senior has a predictor variable, it predicts other things, we're not going to view it as an interval measure. We're just not, for the most part. So for, your two classes, discrete, continuous, discrete, are just categories. These discrete variables are going to be your independent variables. In your continuous measures, your continuous variables are going to be your dependent variables, your outcome measures, right? You can see the differences there. I'm going to tell you right now, I've never been asked after my first class of stats when I was an undergrad in like the year 2001, I have never been asked to define if a variable is nominal, ordinal, racial, or interval. So don't get too hung up on it, but you can see the differences. This is something we're transitioning a little bit in the lecture now to just basic experimental design. And there is something I want to get off my chest. This causes that. This is a mnemonic that I use to remember IV and DV. I struggled with IV and DV when I was in your position. I was always thinking independent and dependent, and I was like, well, the study depends on my manipulation. Well, it also depends on my measures. Independent, nothing's independent here. My manipulations and my measures are connected, so it just didn't make any sense. Let's put that up in a ball, throw it out. This causes that. And yes, I changed the spelling to make it easier to remember. I causes D. Is causes that. Is causes that. And yes, I'm not pronouncing the TH. This is important to me. You need to know what an independent variable and a dependent variable is. And the easiest way is that an independent variable causes changes in your dependent variable. Your manipulation causes changes in your measure. That's how an experiment works. Now, one more thing about independent variables. My students often struggle with their manipulations because let's take a manipulation, a simple manipulation. Let's call it drug dosage. None, one dose or two. And I'm thinking about this in like a rat study, just a simple rat study. Here I just have one independent variable, drug dosage, that has three conditions: no dose, one traditional size dose, let's say 1,000 milligrams, and 2,000 milligrams, right? A lot of my students think that's three independent variables. It's only one. There are three conditions or levels to that independent variable, but there's only one independent variable there. A set of conditions that are in the same category, in this case, drug dosage, are one independent variable. Just don't forget that. And then your measures, a dependent variable is always a measure, and measures are mostly dependent variables. So your dependent variable is always a measure, and measures are mostly dependent variables. We'll get into this a little bit. Now, we understand independent and dependent variables. How do we start to critique them, right? So a good manipulated variable, a good independent variable, a good manipulated variable. I use this terminology. I'll explain why in a second. But manipulated variable and independent variable are essentially most of the time the same thing, but there are some cases when they're not. So a good manipulated variable, one that I'm manipulating, validity, is my manipulation making people feel the way I want them to feel? So I want to make people feel happy. Is my happiness manipulation making people feel happy? Or I want to make people stressed out. Is my stress manipulation making people stressed out? So I'll give you an example of a case of low validity. I'm going to choose to show people movies, the full thing. I'm going to do that in my experiment because I like to make first years upset. It's part of my MO, right? But I'm going to show them either randomly assigned to see the cinematic classic Billy Madison or the cinematic true classic Schindler's List. I think this is a manipulation of happiness. Is it valid? Well, when you actually think about how much people hate Adam Sandler movies, no. It's not really a very valid manipulation of happiness. I'd say there's some validity to it, a very small amount, but it's not perfectly valid and nothing is. But in this case, I think this movie is making people feel happy relative to the control movie, The Schindler's List, which I think is making people feel sad, right? But in reality, these two movies differ in cinematic quality. They differ in the fact that Billy Madison doesn't make everyone happy, right? I would say Schindler's List does make people feel sad. I'd feel more confident using that movie. But is this a valid manipulation of happiness? I'd say there's some questions here and I could do it better. And that's the point. You're looking at variables and you're asking, can I do it better? Yes, we can do that validity. We can make a more valid manipulation of happiness. Reliability of a manipulated variable, of an independent variable, is when the manipulation makes the same person experience nearly the same psychological reality, right? So when a specific level of my independent variable makes the same person experience nearly the same psychological reality, right? Let's take Adam Sandler. I like Adam Sandler movies. Judge me, that's fine. When I watch Happy Gilmore, right, I am going to reliably feel about the same level of happiness every time I watch that movie because I enjoy it. Maybe a little less Maybe just a little bit less from the first to the second. The first time I saw it, it was hilarious. Second time it stayed, second, third, fourth stayed pretty constant, right? But reliably, this movie puts me in a good mood. So I would say it's a reliable manipulation. It's just not valid in terms of an experimental sense for everyone else. It might be valid for me, but it's not valid for all my participants, if that makes sense, right? So in this case, that Billy Madison manipulation is not valid, but I would argue for me reliable, and probably reliable for people that hate it as well. It makes them hate it the first time, the second time they hate it, the third time they hate it, the fourth time they hate it. So that's a reliable manipulation. It reliably causes someone to feel the same way. Now, the only way to know if your manipulation is reliable is you have to add a dependent variable to it. So let's take this Happy Gilmore example. I have to add a measure of happiness, and I have to, give it to multiple people multiple times, showing that the movie consistently leads them to have about the same experience of happiness. More on that in the next slide. Power is the power of the manipulation to observe, to create differences in the psychological state. Right? Here I say the intensity differences between different levels of your manipulation. And I have on here a sort of stress manipulation. So here's a low power. I think this is a manipulation of stress, but I think it's a low powered version of that manipulation. You will have to give a speech to me, your professor, that's pretty cool and chill, in 25 minutes from now. The control condition, you just have to think about stats for 25 minutes. I'll figure out some way to make you do that. This is just sort of like a pilot. This is just like a rough draft of this idea. But to me, that's going to create stress, but it's not going to create a massive amount of stress. So that's low power in comparison to my high power manipulation. Look at how I changed it. You have to give a speech to all psych neuro professors in 5 minutes on statistics. Oh my Lord, you got 5 minutes to do this. You're giving it to people who are like hardcore, like we're going to rip you apart. And you only got 5 minutes to do this on a difficult topic. You are now stressed out of your mind. Control condition. It's a control condition. Think about, statistics for 5 minutes. Which condition is going to make me experience more stress? The high-powered condition. Which condition is better? That's a more difficult question, right? In this specific example, I'm going to run 2 different experiments, one with the low power, one with the higher power. And I'm going to hope that they both work. I really like it when low-powered manipulations work because I can say something like, even in a case of very, very slight stress, we observed the effect we were predicting, right? So that's where the low-powered case is actually good. However, if you don't find an effect, or they don't find an effect, and someone's like, oh, I didn't find an effect, it's not there, and you're looking at their manipulation and it's weak, and you're like, you can strengthen it up. Well, you're not finding an effect here, but that doesn't mean there's not an effect. You can increase the power. So when you see a manipulated variable, think about, is it actually manipulating the psychological state that it's supposed to manipulate? I mean, that's what we're interested in, or the neurological state it's supposed to manipulate. I think my neuroscience majors are going to have an easier time with this because stuff like drug dose, that's easy, right? Stuff like surgery, that's easy. That's easily valid, right? It's not easy to do, but it's valid. Reliability, this is something that we got to test the whole experiment on, right? And it's something that's hard to know. You can either judge it off your gut feeling. I don't think this would reliably make me feel this way. I think there's a lot of, different ways I would feel with this, right? That's one way to think about it. Or you need to check the reliability of the whole experiment. You need to repeat the experiment and get the same result multiple times. We'll go to the second half of that in the next slide. And then power, I really want you to think like sometimes having a tiny difference is good. Sometimes having a tiny difference is bad. Sometimes having a massive difference is good. Sometimes having a massive difference is bad. But you still have to think of difference between not your results, but between the sort of intensity of the manipulation, the strength. This is what I call the sledgehammer. That high power example is the sledgehammer. That's me saying, how can I make these as extremely difficult as possible. The only thing I can think about is like adding some contingency where if they get paid for the experiment based on their level of work, and if they get a C, they get $1, and if they get an A, they get 500. Right? I can still think about how to make it even more intense, more stressful, more important. Right? But these are the three things you think about when you think about every single manipulation. Is it valid? Is it reliable in terms of its effects on the psyche and mind and experience? And what level of power is it at? Could you make it more powerful? Could you make it less powerful? Do you think it would work with less power? Do you think it needs more power? Like, these are things you need to be thinking about. And a good measure also has validity, reliability, and power. Validity of your measure is the exact same. You're measuring what you say you're measuring, right? Ignore that. I don't know how that got on this slide. Ignore that example. But I'm going to give you another example, right? Galvanic skin response is your sweat response. I'm interested in stress. I'm going to measure your galvanic skin response. And I'm going to say in my study, that this is a valid measure of stress. Well, that may be wrong. You may be sweating because the room's hot. You may be sweating for other reasons. So that might be a way to critique the validity of that galvanic skin response measure. Now, the only reason we know it's a valid measure is because consistently past research has shown that when people are stressed, their GSR goes up. So that's perfect. Reliability. Now, this is when you just have a measure, right? When you measure the same person in the same psychological state. Now, most textbooks don't state it this way, but I'm going to state it this way. Because, look, you're a person, you have different emotional states. I should be able to make you feel different emotions. So, I need to make sure that when I'm looking at the reliability of my measure, it's in the same psychological state. So, when I measure you in the same psychological state that you are in now, hopefully I created it with a manipulation, right? See? Or I created it with just like a control variable where everybody watches March of the Penguins, which is something they do in cortisol studies because it's the most boring, calming video that exists. Side note, right? Only in that condition where you're in the same psychological response, same psychological state, do I get the same in an ideal world or similar results. Similar is okay. In order to test reliability you can kind of do it alone. You can give a measure multiple times to the same person. But another way to test the reliability of your whole idea and your whole study is to replicate your study, right? The more times you run your experiment and find the same result, that's reliable. You're reliably getting the same result. And I think people forget that. That's the best way to measure reliability, is to show the same effect over and over and over again. This is why psychology studies often have 5, 6, 7 replications in one paper, because that's super important. And then finally, we go to power. And power in this case is a little different than power in that case. They're related. I'll tell you how they're related in a second. But power of your measure is like the power of a microscope. The higher the power, you can detect the smaller and smaller changes, right? So let's use that galvanic skin response example for stress. In that specific measure, I might be able to measure a 1/1,000,000th increase in stress, right? I might be able to see that on the measure. However, when I ask you how stressed you are on a 1 to 7 scale, you report 1 on both trials, right? Because that galvanic skin response has the ability to detect even more than your conscious brain knows about your own stress. That's what we're thinking about in terms of power. Do we have a measure that can detect the slightest changes, right? I think 1 to 7 measures, 1 to 10 measures, Likert scales, I think they're really great. I do. But I also recognize that things like the galvanic skin response is going to have more power to detect an effect at the trade-off of validity. Is it just because it's hot in here? It can detect sweating really well, tiny changes in sweating, but is the sweating due to the stress, right? Hopefully my experimental controls take care of that. But, these things are related. Reliability, the only way you know it's reliable is if you give the measure multiple times to people in the same psychological state. and you see very similar responses. A better way to measure reliability is just to do it at the experimental level and say, does this experiment replicate? Right? That's reliability. This experiment, when I treat people in the control condition and I treat people in the experimental condition, they reliably show differences on my dependent variable. That's the best way to get at reliability. That's the best way to test. If they only found it once in their study, question it. It may not be reliable. But overall, right, if you have power of your manipulation, which we go back and we're thinking about, wait, what's power of our manipulation? Well, that's the strength of the difference between the conditions, right? Like our control condition or our experimental condition is drastically different than our control, extremely different. The more extremely different it is, the more likely we are going to be able to find a difference between the two groups. Likewise, the more sensitive our measure is, the more powerful it is at detecting changes, the more likely we are to be able to find a significant result. I know y'all know what significant results are, but that's where power is. Validity is basically you just got to eyeball it. And if it, like this is where most scientists argue. It's like, I don't think that's a valid measure of stress. I don't think that's a valid manipulation of stress. You've got to eyeball that. But the other two, you can actually think about in more concrete terms, right? Like, if I have a very strong difference between my groups and I have a very sensitive measure, I will find a significant effect. If you don't, guess what? You're underpowered by definition, right? Or there's no effect. But we'll get to that later. Nonetheless, when you are looking at an experiment, you need to just think about the IV. Does it have validity, reliability, power? The DV, manipulated, measured variables. The DV is the measured variables. Is it a valid measure? Is it a reliable measure? Is it a powerful measure? How can you improve power? As scientists, we want to improve studies. So in our study, how do we improve the power of our manipulation? How do we improve the power of our measure? Validity is kind of easy. It's like, well, it seems reasonable. Reliability, that one, we can have a gut feeling on it. I believe this watching Billy Madison will make me consistently feel happy. Or I can just show that my manipulation causes changes in my dependent variable over and over and over again, and then it's a reliable experiment. This leads nicely to our types of experiments. A true experiment where you have at least one manipulated variable and one measured variable. Your IV is a manipulated variable. Your DV is a measured variable. And you can say cause. I'm not going to talk about this too much. Now, a quasi-experiment, you technically have two measured variables, but one is categorical, like our gender example earlier. So, the IV, it's a measured variable that's categorical, discrete, right? Nominal, those sorts of things, right? And your DV is a measured variable that's continuous. Now, this is a correlation. You can't say cause in this case. It is a measured variable. It is categorical, but you didn't cause people to have their specific gender. And that's just something you can never do. So a quasi-experiment's really a correlation, right? And, like it's those of you that have gender in your studies, you can't say gender causes changes because you didn't manipulate gender. So you can't say gender causes changes in your DV. And then you have your correlation. You can argue that the quasi-experiment before is a correlation. Now we would use a different type of test. We wouldn't use a correlation for that example, okay? And that's why we call it a quasi-experiment, but you can think of it like a correlation. You're just measuring two variables and seeing how they're related. In this case, it doesn't matter. Your IV and your DV are interchangeable. Variable X can be the IV or it can be the DV and vice versa. Correlation is not causation. However, we need to think about this because we're scientists. It's possible that X causes Y, Y causes X, Y causes Z, which causes X. Z causes both Y and X independently, right? we need to realize that there's a lot of possible causes here, but we don't know the cause in either the quasi experiment or the correlation. Now, the quasi experiment, it just looks like an experiment. On the surface, there's different groups and there's different measures, and it looks like a true experiment, but it's really a correlation if you look underneath the hood. A correlation is just a correlation. Two measures, are they related? And a true experiment, does my manipulation cause changes in my DV? Super simple. Now, here's where I'm going to critique my students in general, and I want you to critique your ability to think freely. Now, I know right now, if I say correlation is not blank, you'll be able to fill in the blank. Causation. In fact, I've actually been in intro classes where I've stood in front of the class and just said, oh, correlation is not, and just waited. And half the class who never took psychology, half the class who never took psychology before, filled the blank with causation and they were done. Now, I don't like this. This is not free thinking. And it's not free thinking because you're not being scientific. You're just writing off correlations like they're not important. Correlation is not causation. Yeah, I know. Coffee is not soda either. Metamucil is not cereal. You can literally replace two things that aren't the same in this phrase and say it all the time. Dogs are not cats. Yes, of course. Correlation is not causation. But for every correlation, there's a cause to discover, right? Is it that X causes Y? Or does Y cause X? Or does Z cause both X and Y independently? Or does X cause Z, which in turn causes Y? Or even the one that's not on there, does Y cause Z, which causes X? Right? As scientists, we can't just sit there and yell at people, correlation is not causation, right? We don't do that. Correlations get published all the time. They're not like inferior, right? We need to then figure out the cause. And the only way to figure out the cause is to do experiments. But when we find a correlation, we know that something exists in the world. Right? Like there's correlations can tell you stuff experiments can't. We can go out and measure two things in the real world and say, in the real world, there's a relationship between these two things. You can't do experiments in the real world very easily. So like to put off correlations is, I guess I take offense to it because what my research that I did, that I'm kind of moving away from a little bit, but it's what I'm known for, is I looked at correlations that existed and they showed that in hospital settings, Black patients got worse treatment than white patients. And this was a correlation. They just measured race. They measured quality of treatment. They held some things constant. And that's a correlation telling me there's a problem in this nation with racism in the healthcare system, right? That's where my research kind of started from, was a correlation. And then I did experiments that showed that I can say that race caused, because I manipulated race, so I showed that manipulation of race caused worse treatment, and I also was able to manipulate empathy and show that this was due to empathy. So I was able to find a complex causal pattern with experiments, but I started with a correlation. For every correlation, there's a cause to be found. All right? So I need you to think freely. I need you to think critically, and I need you to not just repeat rhyming chants. Rhyming chants, there's one exception that I'll come back to that in a second, but rhyming chants seem more believable. They're more persuasive. Anybody who's taken social psychology can tell you that. So when you're sitting there saying correlation is not causation and it rhymes and it's good and you're chanting it, your brain's shutting off and you're forgetting the fact that for every correlation, there's a cause to be found. And yes, you're going to have to use experiments to find that cause, but that doesn't mean that those correlations are bad. Those correlations can tell you real world problems, all right? Real world relationships. Now, I know you have your experiments designed, so don't get mad at me, but when you can run a within subjects manipulation, why? Because it's just better. It has more power. Literally, when I am my own control, you are removing all individual differences from the data, because I am the same in both conditions. It is not theoretical. Like, I am the same person from trial one to trial two, a few exceptions, but I'm mostly the same person. It is way more powerful than between subject study. You have so much more power to find a difference if there's one there, that it makes sense to always run it within subjects manipulation if you can. You should know the difference between and within subjects manipulations. Between is when you have different people in the different levels of your independent variable. Within is when you have the same person in all levels of your independent variable. Within subjects manipulations are statistically better. They're more likely to find a significant effect. They have more power, more likely to find a significant effect if one exists. So they're beautiful, right? Now I get it. Sometimes you can't use it within subjects manipulation because you'll give away your hypothesis. This is often the case in race researchers like myself. Like, oh, I want to show people like white targets and black targets. I want them to treat these patients. Now, they may get an idea of what I'm doing, and then they may alter their behavior to make them look less racist. That's what's going to happen in race research, right? So, I either have to use between subject studies there, which is fine, or I have to figure out some creative ways to hide my pairings so that they can't like match up which target goes to, which black target is paired with which white target because they're controlled to have like the same facial response or something like that, right? So what I have to do is just kind of overload them with stimuli. I can have a lot of different black and white faces and see if, and just sort of be able to hide those comparisons. But if I only have two faces, one black and one white, I mean, that's not hard to remember what my answer was on the previous trial, right? But if I have a lot of different examples in there and they're all kind of mixed up, it's easier. A lot of different trial types, it's easier to hide my hypothesis, right? Essentially, you don't want to use it within subject study, not only when person is going to know your hypothesis, but also when experience to the first trial is going to drastically alter their experience to the second trial. So I'll give you an example. In my own research, I had participants either imagine how their patient's pain affects them, that was to increase empathy, or in the control group, they were asked to try their best and make their best treatment decisions. Now, I had to use that as a between subject variable because I thought as soon as I told any participant about empathy, they would be engaging in the empathetic practices, right? So if they got the empathy intervention first, and then I told them to do their best, they would just be doing empathy and trying to do their best. That's not what I wanted, so I couldn't run it that way, right? So I made that decision to not use it in that case. But through this process of me doing this research, I fell in love with within subjects designs. And I've also realized and kind of created my own design. I'm sure I'm not the first person to see this out. And there are, I think it works in the Latin square and other things like that. But I'm gonna simplify it for you here. I've made a within between subjects best of both worlds type of experiment. So let's just take this two group experiment. I just have two conditions they're exposed to. Let's say that the Adam Sandler video and the Sophie's Choice or, whatever. Like they got happiness and sadness conditions. I'm going to get my happiness and sadness conditions. Group 1 sees happiness first and sadness second. Group 2 sees sadness second, then happiness first. The traditional way to analyze this would be to ignore the order and just sort of average the scores when people were seeing the happy videos and then compare those to the average of the scores when people are seeing the sad videos. That's a traditional way to run a within subjects analysis. However, if in this example you can clearly see it, couched inside this within subjects analysis on the first trial is a between subjects design. So, right, on the first trial, why did it do that? No. On the first trial, exposed to the happiness condition, half the participants are exposed to the happiness condition, and half are exposed to the sadness condition. I can ignore these responses and these responses because they're not pure, and I can look at the pure between subjects response, right? So I can actually run a between subjects analysis on just the first sort of exposure, the first target exposure right there, the first this versus this. I know you can see that, so that's great. That's it. I can run that as a between subjects design, and I can run it as a within subjects design. I can report both analyses. In an ideal world, they both work. It's also, yeah, I just find that to be a lot of students are scared of within subjects designs, and rightfully so. Rightfully so. I've made decisions to not even try to use a within subjects study, but this right here has given me a little bit more faith in running within subject study, because the worst thing that happens is, let's take group one, this happiness condition, affects the sadness condition, right? That happens. Or in group two, the sadness condition affects how they respond in the happiness condition, right? That's totally fair. But I also have a true experiment right here where I can compare these two groups. So this is the best of both worlds. And sometimes we just have to think creatively. I can actually legitimately analyze this as a between subject study and a within subject study. And I think doing that makes me more confident in running within subject studies. But then it allows me to get the power out of those studies. And I think that's great. What you'll see at the end of this PowerPoint slide is just the easiest problem set of the semester. You're going to apply these concepts that we just learned to your independent project. So, first thing, I just want to know what you did in your independent project. Here I didn't follow my own instructions. I'm kind of racing with time to get this out before the semester starts so you can see the video, decide if you want to stay in class. But okay, so provide a short narrative description of your study. And here you got mine. And really just choose one dependent variable. Here I actually reported two. That was what I failed at. So I manipulated race by showing participants people of different races expressing pain faces of equal intensity. They see all the faces. So every participant sees all the faces within subjects design, right? And here's the measure I measured gender with the following scale, right? And I also measured perceived intensity of the pain by having participants rate the pain intensity of each photo on a 1 no pain to 10 excruciating pain scale. Okay, so really you can cut out the gender example there. I didn't find anything with gender in my research. I was just putting it in there as an example of like a discrete variable, a nominal variable. But that's gone. Following my own instructions, I just have that first and last sentence, and I just described my study. Please describe your study to me. Maybe give me a little bit more so I can, like if it's weird, so I can really figure it out. If it's simple, if it's a listening to music under different distractions, just be super clear, because I want to get to know your studies too. All right, so for each variable, you got to give it a name. So I have two variables here, and you all have an independent and a dependent variable. So give it a name. My first one is patient race. Is it independent or dependent? It's independent. For independent only, is it within or between? Well, it's within because they see all the faces. I gave a little clue there. Is it discrete or continuous? Well, that variable is actually discrete. It's my grouping variable, target race. For discrete, is it nominal or ordinal? Nominal. That's mostly going to be nominal. For continuous, is it interval or ratio? Well, it doesn't include 0, so it's interval. Analyze the variability in terms of validity, power, and reliability. This one, you can see my written examples in the final one. I'm not going to go into that. Describe one predicted main effect in terms of cause. So here you actually have two independent variables and all that stuff. Maybe that's what I was thinking with that measured gender variable. Yeah, that actually does fit. So I would have like patient race, participant gender. So leave that in there. I was wrong. Sometimes you just get scared when you're doing a lecture. And then my measure is that. Well, take your study, tell me your two independent variables and one of your measures. And then for each of those, you're going to give it a name. You're going to do all those steps. You're going to critique it in terms of validity, power, and reliability. And describe one main effect in terms of cause. Like if it's like here, I'd say gender is related to changes in perceived pain intensity, right? Maybe gender is associated with an increase in pain intensity for men. Maybe that's how I'd state it, right? Or I could say, patient race caused lower pain perception. Right? That's all I want. Easiest problem set of the semester. You can see my answers on the last one. All the stuff is posted. This is in my YouTube channel, but the PowerPoint slide itself with its mistakes are all posted on our world class. All right, y'all. Have a good day.